know, she's a student of the University of Maryland in Washington, D.C. And last year, she attracted a lot of attention of the mathematical community by her solution of the Mizohata Takeuchi conjecture, which is a long-standing open problem in harmonic analysis. And today she will explain further the counterexample. This is a joint seminar of the Rubio de Francia seminar and the Human PhD seminar. Know that the Rubio de Francia seminar is probably the oldest math seminar in Spain, and Hannah is very likely the youngest speaker in the more than 1,300 talks that we have since José Luis Rubio de Francia created the seminar in 1978. So we are very, very happy about this. And that's all. Hannah will talk about curves, lattices, and the MT conjecture. So thank you very much, Hannah.
Thank you for the introduction. Okay, hello everybody. Today I would like to tell you about my counterexample, but it takes a little while, so I won't tell you about all of it. The rest will be a secret. You have to check my paper. So let's get started. Okay, so the conjecture is in an area of math called Fourier restriction theory. So it is a question of what happens if you restrict the Fourier transform. Now, a jewel to this question is what happens if you take the Fourier transform of something that is restricted to something. Now, it sounds very abstract. So here's a picture. So imagine you have some hypersurface. I have Rn here. N could be 2 or more. I mean, a hypersurface in one dimension is kind of boring because it's just a point. But so we don't like to think about that. But so today the focus is like, what is a Fourier transform of something that lies on this hypersurface? So here I have this blue hypersurface and the pink region. So if, say we have a function that is 1 on the pink region, and the question is, what does the Fourier transform of this look like? If you are more familiar with analysis, we are looking at the Fourier transform of measures supported on these hypersurfaces. Because, as a technical note, this has measure 0, right? So it really is 0. Everything it integrates is 0. So we pretend that you can either imagine you slightly thicken it, so you slightly thicken your parabola by a very, very small amount, and then you measure the Fourier transform, and then you take a small amount to go to 0. But anyway, that's his technical notes. So one way to ask this is to ask for the size of the level sets. So if we take a Fourier transform, we get a function. And in analysis, we like to analyze the functions by the level sets, or rather the sub-level sets. And so we will be interested in the size of the sets as well as the shape of the sets. Okay, so here's the question. So what is the shape of the level sets? So there's this idea that it should concentrate along tubes, which is the wave packet decomposition, which I believe goes back to Bourgain. And the main idea is that it relies on the uncertainty principle. So what is the uncertainty principle? So if any of you, have some physics intuition, then you maybe know that the frequency and the wavelength will be inverse to each other. And so if we have a very, very large frequency, then our wavelength is very, very small. If we have very, very small frequency, then the wavelength is very large. So if all of our frequencies lie in a small region, then all of the wavelengths will be very, very big. Well, if all of the wavelengths are very, very big, then the function oscillates very slowly. If you take a lot of waves with a very long wavelength, then this means that it cannot oscillate very quickly. So this is sort of how I like to think of the uncertainty principle. So here I have it written. So if it is supported in the set -r to r, so all of our frequencies are bounded by r, then all the wavelengths wavelengths are bounded by 1 over r, or greater than 1 over r, which means that it will not oscillate very quickly. So it's essentially constant on intervals of width 1 over r. Well, or maybe a tenth of 1 over r, because over the whole wavelength it does oscillate, but over just a tenth it does not oscillate very much. But it's up to constants the same as 1 over r. So there's also the higher dimensional version of this. So if all of the frequencies fly in a box, then the Fourier transform will be constant on the dual boxes. And the dual boxes are the boxes with inverse dimensions. So if the x frequency is bounded by a, then the x wavelength is bounded by a inverse. Any questions so far? Okay, so why is this useful? Well, it tells us, like, if we have something confined to this box, then it essentially will look like these tubes in the other direction. Because all of our frequencies are very small in this direction, and so all of the wavelengths are very large in this direction. And so it means that we end up with all of these different tubes. Okay, so the reason why this is useful is if we are interested in the Fourier transform of something on a surface, then we break it up into many pieces. Each of these pieces is like a box that is very small in one direction and very large in another direction. So we approximate it as a collection of these boxes. And on each of these boxes, the Fourier transform will look like tubes going in the other direction. Another way to think about this is if you think about the way that light propagates. Light will be a solution to the wave equation. And so at a large scale, it looks like light goes along these light rays, which are like tubes. And so this is sort of the same phenomenon at a larger scale. But if we zoom in, then light is not really made of tubes. Because light is not, in physics it will say it's not a particle, it's a wave, right? But in any case, this is the principle, that the Fourier transform of this will look like many different tubes on top of each other. This will not be necessary later in the talk. But still, are there any questions? Okay, too fast, too slow? Want me to speed up or slow down? I see a few thumbs up, so. Well, what does this mean? So, you don't need to read this, by the way. What this says is it's measuring the amount of energy on some region. So this E means Fourier transform. It means extension operator, so Fourier transform of something that's on a hypersurface. So if this is made of tubes, then all it is saying is that this is like the tube mass that we measure. So if W is like a set, then we measure how much energy we have on this set W. And so the conjecture says that it will be bounded by the total amount of energy that we start with, which is like this, times the maximum amount that we can get from a single line. So the idea is that if the energy is made of lines, this thing tells us how many lines we have. This thing tells us the maximum energy per line. So the energy should be bounded by the number of lines times the energy per line. Okay, now this is really very much too fast to understand everything here. But luckily for the rest of the talk, you will not need to understand anything that I said before. So, if you have gotten lost, this is the time when you can feel free to come back. So there's this problem here. For some reason, this is an interesting problem. It has applications to PDEs or number theory or whatever. And so we're interested in what cases this can be proved. So, in 1997, Bartolomé and Vega, forgive my pronunciation, have proven that it's true in the radially symmetric case. And there's a more recent result by Tony Hargrave, Marina Indipulu, and Owen Wong that proves that with this loss. So what does this mean? It means that this is not really less than or equal to. It's less than or equal to if you multiply by something else. So if you are familiar with what this means, then I don't know, that's good. If you are not, don't worry about it. We don't really need to understand this for the rest of the talk, but this number needs to be 0. And right now this is 1/3. So they proved it for 1/3, but the conjecture says it must be true for 0. So, yeah. And then Larry Guth has proved that in 2022 that actually 1/3 is the best that you can use using these methods. So to get from 1/3 to 0, we have to use a new method. Okay, if you do not understand any of this, you can come back at the next slide. But still, are there any questions? Okay, I think probably I've lost a lot of people who do not do analysis, but I think you can come back now. Or, well, maybe not, sorry, I forgot. I have one more slide. You can sleep for one more slide. But, so my theorem is that you can, that actually it's not true, because there's this factor here, this log R. So basically R is like, if you consider this problem, but in a small region. So basically what it says is that the number of lines needed is, it grows with the logarithm of the size of your set. And so this would disprove the conjecture. And then more recently I proved with Zhang that it fails with a power of R as well, which is in some sense more interesting because in a lot of areas in analysis, we like to study the asymptotics, and if we can prove something about polynomial growth, it is usually more interesting than logarithms. Okay. Let me check, okay. Okay, good. So you can come back now. Are there any questions though before we move on? Okay, well, this may be a very bad thing if there are no questions. But hopefully we will follow the next part. Okay, so there are sort of a few chapters of how to show this. And today I will only be going over a few of them. I think I will be talking about number 4 and maybe number 5 if I have time. So the main idea of the proof is that you can use duality and you can use Poincaré from Fourier analysis to reduce this to a problem about convolutions and everything you see in frequency space. And then you can make the frequencies like discrete by using these approximations. And from there we get this problem in additive combinatorics. Additive combinatorics is, well, the study of addition, but in a more interesting way than we would normally think, is the study of if we have a set of things and we want to study the structure of the set of all sums of things. Okay, whatever. So in chapter 4, we will talk about this problem about these sum sets. Chapter 5 is about actually solving the problem, which is done using this very high dimensional lattice that we have to restrict to a low dimensional space. And then 6 and 7 are about how do we make this work with a curve. In other words, how does this actually relate to restricting to a hypersurface? Okay, so none of that makes sense. 4 and 5, the ones that I'll talk about, can go by themselves. So none of what we've talked about will be needed for 4 and 5. Are there any questions? Okay, well, I hope this is a good thing and not a bad thing, that there are no questions. Okay, so chapter 4. So I like to think about this in terms of what I will call these coins. So I say that a coin is like a unit mass on a 1/r disk. Now, you can just think of this as a point. And so you can think of it as a point, and what we'll be interested in is the difference set. So, in fact, if you don't mind, I might just switch it up because I think I have a better way of explaining the difference sets somewhere else. Yeah, so here's just from a different talk where I explained the difference set. So in the previous talk, the last time I gave it, a lot of people did not understand. So I'll explain it using these other words. So if we have a set of points in the integer lattice, such as this set of A, B, C, then the object we are interested in is the set of all differences that we can make. So for example, here we have, maybe I can zoom in. So here's our set A, B, C. And from here, we have all of these things here. We have the A minus B is over here, the C minus B is over here, and so on. So I zoom out so you can see all that. So we started off with these 3 points, and then we get all of these 9 points. However, sometimes we get repeats. So for example, 0 is written in 3 different ways: A minus A, B minus B, and C minus C. So just to make this clear, the idea is that we look at the set of all differences of 2 elements in our set. So we have the A minus B, A minus C, B minus A, B minus B, B minus C, C minus A, C minus B, and C minus C. Okay. And so we get all of these 9 points. And in this case, we have a lot of repeats at 0. So I put the number 3 to denote the number of repeats. So I'm actually considering this as what I call a multi-set instead of a set. So a multi-set is a set with repeated elements. Okay? Any questions so far? Okay, so this is one way to visualize it. This is how I did it in a different talk. Now, I will head back to the talk I am actually giving. In this talk, I visualize it differently as coins. So you can ignore the R inverse if you would like, but the idea is that we have these points, which are a set of points in the plane. Now, the main idea is that instead of writing the number on top, we can visualize it as stacking the points. So this is just a different way of visualizing it. So for example, I'd say the difference of these 2 coins is we put a point at the difference of the 2 centers. So a point is just a way that I draw a point here, but I make it bigger so we can see it. So we have a point here and a point here. So we look at the difference factor. So the difference between them is here. And so similarly, if we have a collection of coins, then we look at the difference multi-set. So I want to be careful here because last time I gave this talk, I lost a lot of people. So we have all of these points in R2. And we look at the set of all pairwise differences. Now, the multiplicity of the difference is the number of coins stacked. So maybe I would place 2 points on top of each other, but then we can't see that there are 2 points there. So instead I say, well, let's stack them on top of each other, like points. So, for example, here there are 6 coins, and so over here I have a stack of height 6, because there are 6 ways to get 0. So there were 6 different coins that go at the same point, and so it stacks up. Question?
This is the visual in 2 dimensions, but you are doing it in any dimension.
Yes, but the
this is
talk,
visual. Yeah.
yes, this can be done in any dimension. I mean, I cannot draw in any dimension, though. So we will pretend that we are doing it in 2 dimensions. So for example, there's 2 points here because there's this difference here. We get in 2 different ways. So here to here, this point minus this point, and also this point minus this point. So we stack the points on top of each other. Are there any questions? Okay, and then does anybody have any comments of like a way to make to help it make sense, because perhaps not everybody follows. So if anybody has an idea.
In physics, this is commonly done in X-ray crystallography, things like that, because you have to do the transform to the Fourier transform of the points where the atoms are located in the lattice. I think it's something similar.
Okay, so the comment is that maybe it is similar to like the crystals that people study in physics.
And when you shine X-ray, you get the Fourier transform and bright spots in the Fourier transform behind the crystal.
Okay, so the comment is when we shine in like an X-ray, then we got the Fourier transform behind the crystal. Okay, so I guess I am not really sure how to use this for this part, but if it is useful, then hopefully it can be useful for some people. Yeah, I guess I'm sorry that I don't quite understand, but yeah. Okay, so this is just a way to visualize these different sets. Okay, so now that we're done with this, well, maybe I'll ask one time. Any more questions? Okay, because this part is, oh, yes?
Can I make a little comment?
Yes.
For understanding this, people will not have the high level to understand this. This transform can be similar for looking the roots of a polynomial. For example, I do this connection because you're looking for the points for the difference to make zero the distance of the plane. That will be similar that we can do in other parts of mathematician. We're looking for zeros in planes. No.
So I'm not sure why these are zeros. So I guess here this is a set of points, basically, and we look at the set of all differences of points we can get. So I guess taking the differences of the roots will tell us things about algebraically the roots of polynomials. Is that the comment?
Yeah.
Okay, so maybe some of you have seen this before in that context. I have not studied very much algebraic geometry, so I am not very sure of that. But if that is relevant, that is, I guess, good to know. Okay, so, are we ready? Okay, so let's see. So here's a picture of some different sets. So, we got all of these different pictures. And, yeah, so, for example, if we take, so this is the set from before, up top. If we take 3 points in a line, 3 points in a line, then we get this triangle picture. Okay? So if we take a line, then it kind of looks like another line, but it's higher up. So in general, if we take a subgroup, so a line segment is like a subgroup, but we cut it off. So if you take something that looks like a subgroup, then the different set will sort of look like the same subgroup. So this is sort of important because if we take the line segment, the line is a subgroup, and so we got something contained in the line. So if you're familiar with maybe Luther, that makes sense. If we take 2 lines, then we get 3 lines somehow, because I guess there is this difference, and then there's a difference going in the other way. So we got the points over here and the points over here. And then there's also the differences between these. So we also get the points at 0. So if you are ever lost and you cannot find where 0 is, 0 will always be the highest peak that you see. Because you can always write 0 in many ways by doing a minus a, b minus b, c minus d. Okay. Are there any questions so far? Okay, so let's look at some problems. So I say for any set S, I use this notation S with brackets p minus p is the number of coins in p minus p that touch S. So you can ignore the question for now, but so we would be interested in say for here if we use this curve sigma, then we get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we got 11 of them on here. And on line we got 1, 2, 11, 12, 13, 14. So the question is, if we take this different set, we would like to know, do we get more points on a curve or more points on a line? So I'll say that one more time. So if you take this set over here of these points, and then you take the different set, then you get this blue set. And the blue set oftentimes has interesting structure. And one of the things that we're interested in is it true that we get more points on the curve or more points on the line? And as it turns out, this is actually very related to the Mizohata Takeuchi conjecture from before. Because the idea of the energy concentrating along lines is sort of this line thing. And the fact that it has to come from a curve is like the hypersurface. So a hypersurface in 2 dimensions is a curve. And so this is how it sort of relates to it. However, this is not equivalent to the Mizohata Takeuchi conjecture.
You mean any curve or any line?
So that's a good point. So I mean any line, but in the case of a curve, you could draw a curve that passes through every one of these points. You could do zigzag, right? So zigzag is not allowed because we only consider the convex curves. Okay, so the curves, so you can't, if you try to go around the whole way, then you come back here and then you can't go any further, right? So if we try to do this zigzag, then this is not convex. So we have to look at the convex curves like this, for example, or we could do this one, right? Yes, the curve is a boundary of a convex set. So in this case, I drew it as a subset of the boundary, but you could continue it in any way you want. So you can, a convex curve is also like, if the curve has 2 derivatives, then it will be a curve that's like positive curvature, or negative curvature. It has to be the same. So yeah. So the question is, this blue set can have more points on a line or on a curve? And it is important that these actually have width here. It's because the thing is, we have these points, they have non-zero width. So we just need the line to meet the point at some point. So it does not need to be exactly at the center. It can just be anywhere that touches it. Okay? Any questions? Okay. Let's see how much time I have. Okay, looks like I have about 22 minutes. Okay, so I guess there's no, any questions? I think I have. I can't remember if I asked. But I don't see any questions, but I'm actually very bad at finding all the questions in the audience. So you can always just say your question. Okay, one thing I forgot to mention is this thing here means not necessarily exactly less than, but less than, let's say, up to a constant. So bounded by 10 times this. Okay, so maybe, yeah, so I mean, technically, I kind of think of it as something slightly different, but we will just pretend that it means less than some constant times that. So is it true that it's less than twice the number of the points on the line? Or is it true that it's less than 10? For some constant, is it true is what we wonder. Or can we get like infinitely many times more points on the curve than on the line? Okay, I hope we're good. But any questions?
So you're assuming that the set is finite?
For now we'll assume the set's finite. So when I said an infinite number, I guess really what I mean is an arbitrarily large number, like times more. Okay, okay, so this is actually false using this wave packet decomposition. So the wave packet decomposition, this isn't really the wave packet decomposition, but the whole idea of the wave packet decomposition is to break up the curve into pieces. So this is what I've done here, is I broke up the curve into many pieces. So remember these line segments, they're like these subgroups. And so if we take the difference set, then it will also look like a line. And so it turns out if we do these sort of pairs of these line segments, then we can get it to like be translated over here. So then we can sort of get it to follow this curve a lot. So by the way, this is not the entire difference set. If I drew everything in the difference set, then I think it will break my drawing app. But this is sort of the general picture of what it will look like. The difference sets between two of these will look like these funny parallelogram things. But the main idea is that we have a lot of this hall, there's a lot of points on this curve. And since we have so many of these line segments, if we try to get a line to pass through it, maybe the line is parallel to this one, but the line cannot be parallel to all of them, and so we can only get one of them. It is not, if you do not understand this example, then you can still understand the rest of the talk. So don't be afraid. But if you have any questions about that, then you're welcome to ask. Okay. I think this takes a while to understand also, so I do not expect everybody to immediately understand this. So this is not the counterexample that I came up with, because it turns out the wave packet decomposition is not sufficient to prove it. Because remember earlier I said this is not exactly Mizohata Takeuchi. So I will tell you something that is similar to Mizohata Takeuchi. So I say that this configuration has low, I call it incidence density, which is why it's not a counterexample. So what do I mean by incidence density? So it's a word that I made it up, and it just means sort of how tall these stacks are. So like, in other words, if you take a random green point, then a random blue point, then most likely they do not like sort of come from each other. So this blue point, any of these blue points will come from two of these green points. So if you pick a blue point at random and a green point at random, most likely they do not go together. Yeah, so this is a little bit of a technical note, but the main idea is this blue set is too spread out. For the Mizohata Takeuchi conjecture, we want a very, very small blue set, but still many points on the curve. Many points on the curve. So if this doesn't make sense, that's the way to think about it. Okay, so here I explain what it is. So if you take this blue point, which is now purple, then it only comes from two green points out of these. This is a different configuration, by the way. It only comes from 2 out of the 6. So, because this is the difference here, it only comes from either this pair or this pair. So, in a good example, it will come from almost any of these we can get this difference. So in other words, we want very concentrated blue set to lie on our curve. Any questions? Okay, well, okay. So this is the conjecture that is equivalent to local Mizohata Takeuchi, and it states that it's the same thing as before, but I multiply by this sort of incidence density factor, which just means that if we want a counterexample, we need it to be very, very spread out. So, I mean, what is this picture that I drew? Yeah, okay, so for example here, this picture is, you may notice it looks like a hypercube. So, this is actually, I guess hypercube would be in like 4 dimensions, but I think this, no, this is in 4 dimensions, right? Because there's the cube over here and the cube over here. So in other words, I took the hypercube in higher dimensions and I projected down to 2 dimensions. Now, the idea is that a lattice, like, I don't know, if we take the integer lattice but cut off at some point, it will have a very concentrated difference set, because the difference between any two integer, like into any two lattice points will be a lattice point. And so I guess the idea of the first paper was that if we use these hypercubes, then we can get it to concentrate along our curve, because the difference sets on the hypercube will basically look like another hypercube. And so it will be very, very concentrated. And so in this way we can get many, many points on the curve by choosing the correct projection. But you'll see that there are very few on a line. So we have like 5 of these stacks here. And you'll see it's very hard to get 5 on a line. So you could do as many as you want, and then you can use this. So if this construction doesn't make sense, then that's also fine. I think you will be okay later on. Are there any questions so far? Okay, I see a lot of thinking faces and also confused faces. So if you are confused, you are not alone, and I would encourage you to ask a question. But, no pressure, you do not have to ask a question. Okay, but I don't see any questions. Okay. And I have it stated here as a fact that is equivalent to, I say, the local Mizohata Takeuchi conjecture for positive definite ways. And now, if you work in analysis, or maybe harmonic analysis, then maybe this makes sense. But basically it just says that this is somehow equivalent to the conjecture about Fourier analysis for a certain class of weights. For certain cases, this is equivalent. And so if we want to disprove the Mizohata Takeuchi conjecture, we will want to disprove this statement. Now I showed you how to disprove it using a hypercube. But the hypercube will only give us a logarithm many, so maybe we can try for something better. I mean, if that doesn't make sense, I think that the rest of it should still be understandable. So here I go and I calculate this. How much time do I have? I guess I have, my iPad is in the wrong time zone, which makes this very confusing. Actually, no, it is in the right time zone. I guess I have about 10 more minutes. So perhaps I can skip this. This is just a calculation. I guess the main idea is that if you take a random difference here, it only comes from like 3 pairs. And so it's very much too spread out. We need a more complicated example other than this one. Okay. So here I will show you another example. This example, I will tell you, doesn't work. But suppose we have a lattice. So here I have this 4x4 grid. So if you have a 4x4 grid of points, then the set of all differences will lie on, I guess, a 7x7 grid. Now, the reason why is because we have, I don't know, 1, 2, 3, and 4. So our differences can go from all the way from 1 minus 4, or negative 3, up to 4 minus 1, which is positive 3. So number of integers from negative 3 to 3 will be 7. And so that's where we have this bigger grid. So the interesting thing about these lattices is that we get the very concentrated difference sets, because there are many ways to get this. So for example, this difference over here, this one comes from 1, 2, 3, 4, 5, 6, 7, 8, 9. Well, really only 9. I guess 9 out of 16 is maybe good here. But you can imagine if this was a much wider lattice, then we would get closer to the number. So yeah, I guess this is one idea, is we can take this lattice. Okay? So to understand this, we would have to know how many points we can get on how many lattice points we can get on a curve. So on a convex curve, how many lattice points can we get? The answer is, well, the number of points to the power 1/3. It is actually a very interesting construction, and it's kind of just a fun problem to think about for a while. So if you have, say, 10 by 10 grid of points, then how many points can you get to lie in a convex curve? And so if you want to find a solution, you can look up the Yarnik curve. So here, this incidence density factor will be 1 because basically it's very concentrated is what we can think of it as. However, the number of points on our curve is still less than the number of points on the line. So this is the problem with choosing a lattice, a two-dimensional lattice, is that it sort of is made of these lines. So we want something that is lattice-like. So it has to be lattice-like, has to have a lot of points on a curve, and then it also has to not be made of lines. So we have lattice, but many points on a curve, not many points on a line. So these are the three conditions that we have. The technical things, I think, probably, I don't know, make sense to probably not very many people, and so if you do not understand all these calculations that I have written, then don't worry. I mean, you're not alone. But the main idea is just, it's a very concentrated difference set. In fact, I think I actually drew every single point in the difference set, so there's like 256 points, I think. I mean, actually, maybe not. It doesn't look like 256, right? So, I don't know. Maybe I left some out, because I think when I was drawing this, my drawing app actually crashed, because too many coins. Are there any questions? Okay, so my hope is that even if I've lost you, maybe sort of you can still follow the general idea of concentrated different sets and things, but I'm not sure if I will achieve that goal. You don't need to pay attention to calculations, but the idea is the wave packet decomposition, the wave packet thing we did before, works very well to get a lot of points on the curve and not many points on the line. So it's good for curves and lines, but it is not very concentrated. The Yarnik curve I showed you before is very concentrated, but it has more points on the line than on the curve. So we want to sort of combine these things. So this is just a general idea. So I don't have much time left, but if you've been lost before, here is an overview of what we did, so you can wake up. Well, actually, I don't think anybody is sleeping, but so I guess maybe I guess if some things are good in that regard. So we looked at this conjecture about, can we get more points from a curve than on a line? We showed that it's false by breaking a curve into many pieces. And then we say, okay, well, make it harder, because as mathematicians, maybe we like things, if we can solve it, it has to be a little bit harder, so we can't solve it. Then we add this factor, the incidence density, which is just how concentrated it is. And so we look at some examples, and our idea is that we want sort of this random lattice that doesn't have very many points on the line. And I don't know. Actually, points we can get, or it's good if we can get points on a curve too. Okay, are there any questions? Okay, so I don't have very much time left, so I can do a sort of an overview of the next chapter, and how we go over this. Oops, I have to scroll up. So here I do a little calculation. So if we choose a set of points to be a lattice, then we have so many points on a line. So the number of points to the power 1/2. So if we have a grid with k points, then the side length will be square root of k, or k to the 1/2. And and that's the number of points we can get on a line. However, if we do a higher dimensional example, then we actually have very few points on the line, you see here, because it's closer to the cube root of the number of points. So if we use higher dimensions, then it gets better, because in higher dimensions, if you have a grid of k points, then the number of points that you have on a line will be cube root of k. And so you can project this down into lower dimensions, and then you still get a lattice-shaped object that will have not very many points on the line. However, today we'll be doing a slightly different construction to that. Any questions so far? Okay, so just the main idea is we take this set, and what I will do is I will embed R2 inside R3 in a random way. So this plane B is like our R2, and it's random in here. And so some of these balls will touch, and this is how we make our set, by an intersection of the high dimensional lattice with a plane. Okay. And the reason why this works, so the different sets, so this is two subgroups, so R2 is a subgroup of R3 under addition. So this lattice is also like the integer, so it's also a subgroup. So if we do intersection of two subgroups, we get a subgroup. And so it's a little bit like, so this set we have will have a very concentrated difference set because of this. Because it will have to lie on this grid, but since it will also have to lie in this plane, because the difference of two things on the grid lies on the grid, and the difference of 2 points on the plane will lie on the plane. And so this is the main idea. And some of the lines have lots of points, but luckily these lines have a very low probability of being on our plane if we make our plane random. And this is the main idea of the proof. And so, what me and Zhang proved is that with very high probability, we can choose this plane so that it does not contain the heavy lines, the lines that have a lot of these points on it. And so, if you have this result with 99% probability, then you can just take a random one, and then until you get one that works. As long as the probability is positive, you're good. And so this is just the main idea of the proof. So, it's okay if you don't follow all the details. It's just the general idea is that we want these things with concentrated difference sets that don't have many lines. And so we use higher dimensional lattices. Okay, I think I'm done here. So, yeah. Yes, so that would be chapter 2. And so I think that there's a lot of computations. So do I have any nice pictures? No, I don't really have any nice pictures. Okay, but the main idea is just that we have an L2 norm. L2 norm means that we square something, and we'll magnitude square. Now, if we take the Fourier transform of a product, we get a convolution. And all of these difference sets are convolutions, but they're hidden. So this is just a way to think of convolutions, but in a discretized way, so we can use additive combinatorics. And so the idea is that, for example, if we want to take the L2 norm, then this is just the thing convolved with itself. So dual to the MT conjecture is a conjecture that says that if you take the Fourier transform of a set, then if we want to study the amount of L2 mass it has on a hypersurface, this will be bounded by like a geometric mean of the L infinity norm of the X-ray transform and the L2 norm of the object we start with. So in other words, the sort of the L2 norm restricted to the surface is another way of saying, in the Fourier side, we will do convolution with itself and then ask how many points we get on the surface. Sorry, I hope this makes sense. I guess it's hard to explain all the details.
Okay. By the way, does it make sense to wonder whether the conjecture is true for other norms? I mean, you replace it through ILP.
Is that this 2 or this 2? Or I guess maybe it is. I mean, I actually have not thought about that very much. I guess I have a feeling that it is probably either. Well, actually, I mean, I really don't know enough to say. I think the L2 estimate is sort of the most natural, given sort of, I guess, the intuition behind the problem. There are papers that have studied the other norms, and actually, so it is, I think, true. You can use decoupling, which is this technique in Fourier restriction theory. It refines decoupling technically to show a different P, and this is actually how they prove the partial estimate by Tony Carbonini and Título and Glenier. So I guess in some senses it is true, but not in the sense that we want it to be. I hope that makes sense.
Yes.
What was the most difficult part of solving the problem?
I don't know actually. Yeah, I guess I don't really know, to be honest, what is the most difficult part. In some sense, like all the parts, if you reparameterize your solution by like arc length, then like each part is like same difficulty, right? Like it's like if you're following a path, when did you go fastest? But if you just reparameterize your path, then you're always at a constant speed. So I don't know. Maybe I'm not sure how to answer the question, but I don't know. Question?
How did you arrive to this duality and like the idea of transforming the original problem into this intuition of the offsets and the coins and all that? How did you get to that point?
So I think how I got to that point is originally I think I had a different counterexample that was much more complicated, and I think it was sort of this. I think it looked like a fractal. It was all in physical space, and then at some point I asked myself, because it was so hard to prove, and it took like so long for me to convince myself that it works and whatever. And so I was wondering if I can simplify it, and so I decided to take a Fourier transform, and then I realized that it has a similar structure to this, and you can make it still much simpler if like use hypercubes and all that stuff. So I guess I had a different path that I sort of shortened to make it easier, I guess. I'm not sure if that explains.
When you started with this problem, you had the idea that you thought that if a counterexample was needed, or because I guess some people were trying to prove the conjecture. So how did you think that you will find a counterexample and it was not true?
So the question is, I think, why did I try to find a counterexample instead of trying to prove it? Is that okay? So first I tried to prove it, and then I think I can prove it, and then I wake up the next day and I think I can't because I made a mistake. And so then maybe that day I use my mistake and I construct a counterexample. But then I don't know, maybe a few days later I realize I made another mistake, and so maybe now I can prove it. But I still made a mistake. And so you can imagine I go back and forth and back and forth. And eventually it had been a couple weeks without finding an error in my counterexample. So maybe that, I don't know, it was like, I guess. In some sense, one doesn't really know when to try to prove it or when to try to disprove it. but I guess you can sort of go back and forth. Like, if you accumulate evidence for one side, you can try to like prove it, and then if you don't have enough, then you try the other side. I don't know. I think, well, I was gonna say a quote, but I can't actually remember it, so. There's someone, I think, who said something about this. One, you can try to prove it and disprove it. Okay.
Maybe a more personal question. How has your high school education been in the recent years as you have been working on this problem? And because maybe it's not the usual high school we have, most people have. I don't know.
Okay, so I think the question is like, how did